So the talk today, I'm going to talk about, just as introduced, is on stabilizer bootstrapping, which we use as a general framework for agnostic tomography for several different class of states, including stabilizer states, product state, discrete product state, stabilizer product state, and T-dop stabilizer state, like for four classes. And because we can use this general framework to solve agnostic tomography for stabilizer state. So this provides a mean of magic estimation. That's how we name this paper, because we can use it as a general recipe for all this agnostic tomography and magic estimation tasks. This is a joint work with Sita and Harvard and Xian Zhihan from Tsinghua University. Okay, and so we began with a very brief motivation. Um, so, this work is a part of a more general topic, learning from quantum data. I think you guys are very familiar with this topic, and I just briefly mentioned there are like two kind of motivation for learning from quantum data. So from physics perspective, we want to learn from quantum data because we need to learn from it in our labs. We need to do characterization, benchmarking, and verification on our experimental devices. And from a complexity theory perspective, the motivation for learning from quantum data is that when we compare a classical learner, which can only perform a fixed measurement and collect the classical data and do classical data processing, a quantum learner who can perform some quantum operation and quantum data processing before measurement and can choose how to measure, like to choose whether you perform joint measurement or single copy measurement, whether you can perform measurement with quantum memory. So if you compare a standard classical learner with quantum learner, you will find we will find some quantum assisted information theoretical advantages. And this is something that motivates us from a complexity perspective to learn from quantum data. And the most standard task for learning from quantum data is called state tomography. And we have known it very well. So in this task, you are asked to perform measurements on an unknown quantum state, and the final result and the final output of the algorithm should be recovering the full quantum state classically. And it is shown that for this task, even if we can perform joint measurement, you still require like d square, where d is the dimension of the quantum state. It is exponential in the system set. You still require d square sample complexity. And if you can only perform like single copy measurement, you require d cube. So this task is always statistically inefficient. There are several ways to bypass this exponential complexity. So the first method is called tomography, given by Aronson. The method here, so the task here, instead of recovering the full state, you only need to recover some properties of the state. In particular, you are given some observables, known observables, and an unknown quantum state. Your goal is to estimate the expectation value for these observables. And it is shown that for exponential numbers of observables, this task is there is a polynomial sample complexity task algorithm for this task. And another way to bypass the statistical barrier is to consider state tomography not for all quantum state, but for a class of quantum state. For example, it is shown that if you are given a state that is guaranteed to be a stabilizer state or a product state or something like T-dot stabilizer state. So T-dot stabilizer here means a stabilizer circuit with T non-Clifford gate or like T gate, big T gate. So for this kind of states or other examples also include like you are going to learn a state that can be prepared by bounded number of quantum gates, or you are going to learn a state that can be represented efficiently by a 1D MPS. And for all this kind of state, there have been known algorithms for state tomography using polynomial sample complexity. Okay, so in this work, we're going to focus on this task, like so we consider the state tomography task for a special class of states. So there are existing algorithms. For example, for T-dop stabilized states, which means stabilized just as it with stabilized state with T non-Clifford gate. There's a single copy algorithm that can work using 2 to the T times polynomial n samples and also works in this amount of time. And for product state, you can do full tomography on each qubit. And because it is a product state, so we can combine all the qubit together, and the sample complexity and also the time complexity is linear in n. But I should say things are not always so good. And there are some practical issues. So the first practical issues is that the given state is not perfect. Just as I said, in all these existing algorithms, you are assumed to give a state that is a perfect T-dop stabilized state, or you are given a state that is a perfect product state. But in practice, we might have some noise corrupted quantum data, which means that your state is somehow close to a stabilized state, but it is not exactly the stabilized state. There can be some weird noise on this quantum data.
Sorry.
Yeah.
Do you know that I mean the current algorithms to learn? I mean the previous algorithm to learn T-dop stabilized states. I mean, yeah, they were proven to be successful with the assumption of perfect stabilized states. But you know that, for example, they cannot tolerate 1/poly error in trace distance. For example, I mean, if you know that your state is, let's say, I mean, 1/poly close to a T-dop stabilized state.
Mm-hmm.
You are sure that you cannot apply the previous algorithm, or?
I'm not sure if I know like some previous algorithm that is noise robust to any amount of noise. But in this work, we kind of give an algorithm that works for constant noise rate.
Yeah, I think that all the other algorithms are robust for 1/poly error, Anto, I think.
Okay. So there are previous results for algorithms that are robust against 1/poly noise rate, right? Okay, I see. Okay, so that's why we need to consider an agnostic learning setting. So formally speaking, agnostic tomography requires 2 parameters, and this task is defined by Griveau et al. In an earlier work. So in this work, you are given a class of state C, and you are given copies of unknown quantum state rho. You are guaranteed that the fidelity between your unknown quantum state rho and at least some state in C is larger than tau. And the target is to output a classical description of a state sigma such that the fidelity between sigma and rho is larger than the fidelity between rho and the state class C minus epsilon. So this is tau epsilon agnostic tomography. So there are 2 parameters. Like the first one is there are two subtle things. The first one is the sigma. In the proper setting, we further require sigma to be a state in this class C, and this is considered in this work. We focus on this in this work. So roughly speaking, the agnostic tomography task we consider in this work is like you are guaranteed that the fidelity between your unknown state rho and the state class C is larger than tau, and your goal is to find a state in C that is roughly the state that achieve this tau with at most epsilon error. And when tau equals to 1, this is realizable, and this is what we considered before, the noiseless case. When tau is equal to 1, then you are guaranteed that rho is chosen from C. Okay, so the outline of this work, of this talk, will be consisting several parts. The first part is on agnostic learning stabilizer state and the framework for stabilizer bootstrapping. I will introduce this part in detail. And we also have some agnostic tomography result for discrete product state and or stabilizer product states. And we have some agnostic tomography result for states with high stabilizer dimensions, which are also like T-DOP states. These two parts will be a brief introduction, and in case there is not enough time, I will kind of skip them. And also we have some lower bounds regarding agnostic learning stabilizer states. Okay, let's start with agnostic tomography of stabilizer state. So just as how we define agnostic tomography, the formulation for this task is that you are given unknown quantum state rho, and you are guaranteed that the fidelity between rho and C, which is also known as stabilizer fidelity, is larger than tau. And your goal is to output another stabilizer state, sigma, that has at least tau minus epsilon fidelity with rho. And because for this, so suppose you can solve this agnostic tomography task, then you can roughly estimate tau, which is the stabilizer fidelity. So this algorithm also gives you a stabilizer fidelity estimator. And because and this is also a magic estimation algorithm. So what is magic? A stabilizer state can be classical simulable. So it contains no magic. And magic just measure how many amount of your how much of your state cannot be classical simulable, or how far your state is from stabilizer state. And this is magic. So if we kind of know what is the stabilizer fidelity for a given state rho, then you can estimate the magic for the state rho. I should point out that, are there any questions? Oh.
Maybe, okay, can you spend just a few more words why an algorithm for this implies a stabilizer fidelity magic estimation? I mean, it seems standard argument, right? Like a standard reduction, but can you spend a few more words?
Oh, is that so? Suppose you don't know this fidelity tau, you can kind of like randomly guess some tau and then run this algorithm for agnostic tomography task, right? And you can output a stabilizer state sigma that is close to tau.
But, question.
Yeah.
Can you hear me from this end of the room? Maybe I just like stand up. But so I mean, you need something a little bit stronger, right? If you want to do this, because also if the promise is not true, you have to say, or kind of terminate and say it doesn't work. No. Mm-hmm. If you want to do this.
Yeah, but I mean, you can also do something like a binary search.
Yeah.
I think the question is, I had the same question. It sounds like in your task, you need the promise that your state is at least tau close to the stabilizer states.
Yeah.
It sounds like you're estimating something for which you already have a promise. Is it something weaker, or is it? Do you have the ability to test when that?
Or one can abandon when it's larger than tau. That's also true.
Yeah, I mean, like even when tau is unknown, you can do something like a binary search to search for this tau, right?
But how do you do how do you test whether you're above tau or not?
Because you can start with tau, and if that's not work, you cannot find. So after you learn a result, you can measure this state sigma and measure the fidelity between this state sigma you learn and your unknown state rho, right? And
this might be a bit, sorry, this might be a bit of pedantic thing, because maybe well, you'll explain and it'll be clear later on. But the way I understand what you have on your slide is your algorithm will only work if indeed rho is at least tau close to C. Otherwise, you can't trust the outcomes of your.
But you can verify the outcome very easily.
Okay, so but that means it's actually much stronger than what you're showing us, right? You don't need this as a promise. It's you're given the copies of rho, you output sigma, and then as part of the outputs you either output sigma or you output a flag that tells you, oh, rho is not tau close to C.
It's not like a flag, because flag is like what you verify. So this is more like, if you have the guarantee, then we can say our algorithm will success with a high probability.
Okay.
But if you don't have if you don't have a guarantee, you can kind of guess a guarantee and run the algorithm for a fixed number of iterations, and either you don't get an output, or you get some output, but when you verify it, it does not satisfy this tau and epsilon.
Yeah, the point is you can test the promise after the fact.
Yeah, so you can test it. You can easily verify whether your output satisfy this.
You mean you do a swap test after that? I mean, you get sigma and then you prepare sigma, you do a swap test with rho. I mean,
Or you measure a clear for the
okay,
yeah. Your algorithm output let's say sigma, and you then just you know what sigma is, and you prepare like measurement related to sigma to measure the sigma and rho.
Okay, thank you so much. Yeah, it's clear. Yeah, and then you can verify if indeed you are closer.
Yeah. So you can use something like a binary search to actually search for the cracked tau.
Okay.
Yeah. And then you can get tau, you can estimate stabilizer fidelity, and this will give you a magic estimation.
Thank you.
The stabilizer fidelity is used in this work for like regarding magic estimation, but there are also other magic estimation like stabilizer nullity, and this is this magic estimation is not robust, which means that when you add some perturbation on a state with small stabilizer nullity, it can be a large state with large stabilizer nullity. So a very small perturbation will result in a big change in stabilizer nullity. So it's not robust. And there are some other magic estimation like additive Bell magic. This is not monotone, which means that when you perform a Clifford operation on a state, the Bell magic might increase. This is not magic monotone. And there are other like stabilizer ring entropy. But this is not the main line of the story. And okay, so
can you say more what you mean by robustness? Like in what sense?
In the sense that a very tiny
jump up, like it's like oh sorry, say it again.
A very tiny perturbation will transfer a state with very small stabilizer nullity.
Yeah, okay, that's what I thought. Okay, good. Yeah.
Yeah, but I mean, you can smooth it, right? I mean, the stabilizer nullity, you can smooth it, and then I mean, this is a standard argument that I quite don't like.
Yeah,
I mean, it's trivial that it's not robust as the rank, right? As the
Sure.
how it's called the
I think we receive an email from you like telling us some story about this. Actually,
yeah. Yeah, I mean, there were quite some imprecisions. That's why I wanted to, let you know how the story worked.
Yeah. Thank you for your email. Okay, so our results regarding agnostic tomography for stabilizer state is given as follows. So before giving our result, we just briefly review some previous results. In 2008, Aronson and Gottesman, given that tau equals to 1, which is not agnostic setting, it's like realizable setting. They show that if you are given a perfect stabilizer state and you want to learn this state, then n square numbers of single copy measurements or linear numbers of joint measurements on multi copies are enough. And in 2017, it's later shown that linear number of 2 copy measurements for the realizable case is enough. And the starting point for agnostic setting is a work from Sebi et al. In last year. And they show that for tau larger than cosine square pi over 8, which is roughly 0.85, then they have a polynomial time algorithm to learn the state. And they also give another algorithm showing that for any tau, they have an algorithm that works in poly 1 over tau, poly 1 over epsilon, and poly n copies, but the running time is exponential in n and 1 over tau. So you see, either you have a, so currently the efficient algorithm either require a very large tau, at least 0.85, or you need an exponential time. So the natural question is, can we improve this? And we give an affirmative answer to this question. We show an algorithm that solves this tau epsilon agnostic tomography of stabilized state in polynomial and polynomial 1 over epsilon times 1 over tau to the log 1 over tau. So you just look at this term. 1 over tau to the log 1 over tau is roughly 2 to the log square 1 over tau. So this means that when tau is larger than something that is this sublinear or quasi-linear? But not as good as linear. It's like between polylog and linear. And if you have something that is inverse, exponential to the minus square root log n, then our algorithm can give you an efficient algorithm in both sample complexity and time complexity.
And this works for any tau, right?
Sorry?
This would work for pretty much arbitrary choices of tau. Is that right?
Yeah, as long as yeah, for any tau, the algorithm always work in this this. Yeah.
Okay.
I'm just saying, like, when tau is larger than this threshold, then the algorithm is using polynomial time.
Wonderful.
Yeah, and when tau is inverse polynomial, then this algorithm is quasi-polynomial.
And I'm not sure, like the previous work, maybe GIKL was for pure states, maybe, is it right? Yours is general for also mixed state?
Yeah, but I should say, like, in their work, their algorithm works for pure state, but in a later work, I think in a later work where they proposed the agnostic tomography stuff for stabilized product state. I mean, a different work. They show a reduction from pure state to mixed state.
Okay.
So actually, their algorithm can be extended to mixed state if you combine their two works together.
Okay, great. And your work is in the general mixed state scenario, right?
Yeah, yeah. Our algorithm works for general mixed state.
Okay, thank you.
Can I ask a naive question? Because so this estimation is great, the stabilizer fidelity, because we never expected it would have been measurable because it's extremization procedure. So I always liked it, but I'm confused. So is it a unbiased estimation of it, or it's biased? I mean, can you clarify this point if you know it, of course?
Okay, whether this estimator is biased or unbiased. Well, it's hard. It's hard to say because, like, this theorem, it just as how as I said, the reduction. But this theorem works in the case when you kind of fix a tau, and then you can search for tau using binary search.
Yeah.
I'm not sure if this algorithm is an unbiased sense. Okay.
Yeah, it's a tricky question. I mean, I'll try to figure it out.
I'm not sure if in this sense, like, you are doing binary search over all the tau, and every time you fix tau and run this algorithm to verify whether this is a biased or unbiased estimator.
Okay.
But when you're caring about biased or unbiased estimator, are you like saying there are some lower bound from a metrology perspective?
No. It was just a question out of curiosity, actually, not for some other purpose.
Okay.
I think you
last email.
no, but I think you cannot know. Is probably the answer, because there's always this case where your algorithm is kind of failing, but you don't see it in a certain sense, no? So I mean, it could be that it's actually tau close, but still it's not in the it works with hypermobility part. So it could actually fail to produce a state which is close, and then you think the stabilizer fidelity is actually smaller. And I think all of this gives you probably some sort of bias, but you can probably minimize it by running it multiple times. So I think it's probably biased, but it's not like something that you quantify easily.
Okay, thanks, Johannes.
And sorry, Weiyuan, I have another question. And so yeah, by the way, so if we're doing yeah, like if we're doing first submit a question, like do you like questions along the way or?
Yes, sure. It's okay to ask any questions.
Because if it's too much, we can also postpone some questions. But if it's fine, we can continue. Like okay, like
Fine.
so you said that agnostic tomography of a class of states implies a magic state, magic estimation of class fidelity for that class of states. Right? And this seems to hold for not only for stabilizer, for general class of states. I mean, I want to ask, agnostic tomography algorithm, what is the relation with the tolerant testing? Also implies an algorithm for tolerant testing or?
Tolerant.
Or seems related? I mean, can you just clarify if you have an agnostic tomography algorithm, what you also have? You have the magic estimation, and you have also something else like testing tolerant, or?
I think like
so.
tolerant testing is a testing algorithm, so you are not asked to find the. You are not asked to find the solution, the solution for the state. You are not going to output a state, right? You only need to verify if your state is tau1 close to a class or tau2 far from the class.
Okay,
yeah, so testing should be easier, right? If you have a method that estimates the distance, then you can in particular test, but you expect this to be overkill for the testing task.
Yeah. So I mean,
there's later work from Srinivasan and others that shows they have a testing algorithm for stabilizer fidelity between inverse polynomial and another inverse polynomial. There are some relationship between two inverse polynomial, but they show a polynomial time algorithm to solve this tolerant testing problem.
And okay, your algorithm can also solve a tolerant testing problem.
But still you require tau to be larger than this sublinear value.
I see. Good.
Make it.
And also probably tolerant testing implies magic estimation, maybe. But that's maybe. Is it right? Just for curiosity. Do you know? Yeah. You can do this binary search algorithm if you have a tolerant testing. Can you make this analogous binary search argument with a tolerant tester to have a magic estimation?
I think usually this is the case. Tolerance, like tolerant testing and distance estimation are like somewhat equivalent because of the binary search, as you're saying.
Okay, so if basically you said that tolerant testing algorithm is cheaper than this, and so can give a magic estimation more efficient than this.
I think not for their tolerant testing because they require some condition on tau1 and tau2. They assume that tau2 is at least tau1 to the c for some constant c. So which means that you cannot arbitrarily choose the two threshold for tolerant testing in their algorithm. So you cannot directly use their algorithms for a binary search.
Okay, thank you.
Okay. So let's draw a figure on this on all the content in this page. Like the previous result, we know efficient algorithm for tau equals to 1 equals to cosine squared pi over 8. And for this work, we improve from this point to this point. We show that there's an efficient algorithm until inverse sublinear. And what we don't know is whether there's an algorithm that works for larger, that was for smaller tau. But later we'll talk about this when we are talking about lower bound. Okay.
What's the x after the x?
What's after? Where's the x?
The cross. The cross. The exponential.
Yeah, inversely.
Sorry.
Like this is decreasing tau.
Yeah.
And we show there's an efficient algorithm before this point, to the left of this point. And later we will show that there's some lower bound for super inverse polynomial.
Okay, perfect.
And this actually leaves an open question for inverse polynomial, whether there's an efficient algorithm.
Thanks.
Okay, we are going to talk about some details on proving this theorem. Before talking about some details, I will have to introduce some math, and that's kind of, I know it's boring, but kind of introduce some.
Yeah, it's not boring for us. We love it.
Okay, so what we consider in this work will include something about polystrings and include something about Weyl operators, which is the general. Sorry.
Just continue.
We include some Weyl operators, which is a generalized version of Pauli matrices. You can use a 2n bit string X equals to A and B to define a Weyl operator, and you can just regard Pauli's matrix as some version of Weyl operators. And it is important to notice that for Weyl operators, Wx tensor Wx will commute with each other, and they're simultaneously diagonizable in the Weyl basis. And this also holds for polystrings. And also we define the Weyl basis, general Weyl basis, and n-qubit Weyl basis by performing this Wx on n EPR pairs. So Weyl basis phi x equals to Wx times n EPR pairs. And we define stabilizer group, which is a commuting subgroup of all the string X. And given a state, we can define its stabilizer group. That it is the group of Weyl operator that stabilize this state, which means that the group of Wx such that Wx times rho equals to plus or minus rho. And for stabilizer state, they have n-dimensional stabilizer groups. Yeah, it roughly just says that for any stabilizer state, you can find 2 to the n Pauli strings or 2 to the n Weyl operators that stabilize it. And this Pauli strings or Weyl operators will form an n-dimensional stabilizer group. Okay, these are some concepts. And let's talk about the realizable algorithm. So how does this realizable algorithm work? So the first observation for the realizable setting is that if you are given an unknown stabilizer state, then learning the stabilizer state is equivalent to learning the stabilizer group of this state. Once you know the stabilizer group for this state psi, then you can measure the state. Then you can uniquely fix what is exactly the stabilizer state for psi. So how to learn a stabilizer group? One particular way is to sample from this distribution, phi Wx phi square, sampling from this distribution of Cx. Because when Wx is in the stabilizer group of phi, then this value will be 1. And you will find that this probability distribution will be uniform on the stabilizer group. But if Wx is not in the stabilizer group, then this will give you 0. The probability will be 0. So this is known as Bell sampling. So if we can do Bell sampling, we can sample from this distribution. Then using like linear numbers of samples with large probability, we can find the stabilizer group.
By the way, it's maybe a pedantic comment, but nothing is so special about qubits here, right? This would also work for other finite dimensions, right?
Wait,
it's also not so important.
I
don't want to derail this, sorry.
Really works for other dimensions? Like for general, are you saying like general version of Pauli matrix? Like qubits? Are you
well, I mean, but there's two ways of generalization of Paulis, right? I mean, the dimension 2 Paulis are special that they're both a unitary operator base that's Silberschmidt orthogonal, and they are like a nice operator basis. And for higher dimensions, you have to kind of decide what you want. But we can also discuss it instead. That's not so important. It came to my mind.
But okay, I don't know whether like Bell sampling works for high dimensional Pauli strings.
Oh, it does.
Yeah. So our goal is to sample from this distribution CX. But how can we sample this distribution CX? One way, the standard way, is to measure a two-fold state, phi tensor phi, in the Bell basis. So if we measure phi tensor phi in the Bell basis, what's the result for getting a particular X? We can compute it. The probability of obtaining X is roughly some phi Wx Wy phi square over 2 to the n. And the distribution is actually some Cx plus y for an unknown y. Oh. So we want to sample from Cx. But if we measure phi tensor phi in the Bell basis, we will actually sample from some Cx plus y for an unknown y. That only depends on this phi. So how can we solve this problem? How can we sample instead from Cx? The observation here is in the bit string language, x1 plus y plus x2 plus y equals to x1 plus x2. So now we can choose x1 to be x and x2 to be 0, which means you perform this Bell sampling twice, and the first time you only consider the output x, and the second time you consider the output 0, and the probability of getting this kind of output is a convolution for all y, cy times cx plus y, and you do convolution, and it will exactly ends up in cx.
Yeah, but by the way, to answer my own question, I think the former part would work for any dimension, like the Bell sampling part, but the latter part is not obvious. You might need more settings of the observation true type. I think that should answer my own question.
Yeah, but at least this algorithm cannot. I don't think it can.
Yeah. Okay. Wonderful. Thank you.
So by performing Bell sampling twice and do convolution, just as I said, we can actually sample from this distribution. Oh, sorry. And because, just as I said, Cx is uniform over the stabilizer group, then if you can sample from this distribution, then linear numbers of samples is enough for find out all the dimensions for the stabilizer group, and you can learn this stabilizer state. And this is what's happening for the realizable algorithm. And this step, the solution step, is also named as Bell difference sampling. We kind of generalize it. So in the previous slides, it's only pure state, but now Bell difference sampling, we consider it for general state row. Bell difference sampling will perform Bell measurement twice on this row, and if we just denote the output distribution to be Q row X. For the pure state, it's just convolution between 2C, just as we said in the previous slide. But for general row, the general row, we don't know what is it, or how to generally represents this Q row. And there are two properties for this Q row. The first one is Q row is heavily distributed over the correct stabilizer group, which means that for a stabilizer state phi, the support on the stabilizer group for this phi will be larger than the fidelity between phi and rho to the fourth order. So it is heavily distributed. And also Q row is evenly distributed over the correct stabilizer group, which means that for the closest stabilizer state phi star and any substate, any subspace of the stabilizer group for this phi star, you will find the support on the stabilizer group other than this subspace is larger than 0.1 times this value. So you can roughly think of this. Because V is a subspace of W, and W is like n-dimensional. So V is at most like n-1 dimensional, and V contains at most half of the elements in W. So this is actually means that if you if you pick up half of the stabilizer group, a smaller dimension subgroup, and you consider the support of Q row on the remaining elements, it will contain at least 0.1 times the total support. So this is why it is called evenly. Okay, and these are two properties we will be using many times in the future.
Yes, sorry, can you go back to this slide? Okay.
Yeah.
So like in the previous slides, you showed how to have a sampling from the Pauli probability distribution for a stabilizer state. Here, it's you are describing a procedure which was sorry, can you explain again this slide? You are assuming that there is a state, a stabilizer state close enough to rho, or what?
I mean, this is just generally saying any rho. Like
Okay.
for any rho, if you perform Bell difference sampling, which is this line, this is solution line, perform Bell sampling twice and do convolution. And this is called Bell difference sampling. And for any general rho, if you do Bell difference sampling, you will have the following two properties.
Okay. Sorry, so like in the previous slide, so you do Bell difference sampling twice, and then what do you do? Like,
sorry, but can I? I think that what Antonio said is kind of true. No, if there is not a phi that is an stabilizer state that has large fidelity with rho, then these inequalities are not useful, right?
But these are general. But if there's no that achieve a large fidelity, then
these are general. But I think what Antonio said, I think I share it. No, would you agree? If you don't have, if rho is not has not large fidelity with a stabilizer state phi, this will not be useful. No, or
yes, then this stuff will be very weak. Like it will indicate nothing.
Yeah. Okay. Thank you.
Yeah, but this is general. But this works for general rho. Yeah.
So sorry, like, yeah. The convolution part. Yeah, can you explain? After that, you do Bell. You take two Bell samples. Like what you do?
So suppose you want to sample Cx, then you just consider the output 0 in the first Bell sampling, and consider output x in the second Bell sampling. And then you do convolution for so you just so the probability of getting Cx is the probability of getting 0 in the first time and x in the second time.
No, okay, so you multiply these two outcome, and you take you construct an unbiased estimator, a sample based on two sample, or like a sample from the power distribution based on these two Bell samples.
Yeah. We're just doing a convolution on the two samples. You sample from the two Bell samplings.
Okay, thank you.
Okay. Okay. So now let's talk about how agnostic learning. So the previous one is for realizable setting. Now we just start to talk about agnostic setting. So for example, just give a very simple example. Like you are given a state that is a superposition of 0.9 O0 and 0.1 O plus. Of course, this is a signal part, and this is and O0 is the closest stabilizer state to this state. And our goal is to recover O0 state, right? And suppose we can do Bell difference sampling for many times. We just noticed that so the problem is that you have 0.9 the correct signal with 0.9 probability you will get polystrings for all zeros that stabilize all zeros, and these are what we need. But also with a very small probability you will get polystrings that stabilize all plus state, and this will, and this is the incorrect part. So how can we filter out the incorrect polystrings? We just need to notice the correlations. So if you consider this state rho and you consider this correlation trace p rho square, you will find that for all the polystring that's stabilizer all zero, that stabilize all zero, like ZZIZ, like ZIZI, like all the polystrings in IZ in IZ basis, then the correlation is larger than 0.5. Exactly there, like maybe 0.81 or something. But for all the incorrect polystrings from IX or like from IY, that corresponds to this part or other part, you will find the correlation P rho square smaller than 0.5. So for very large tau, you will find 0.5 to be a borderline between the correct polystrings and incorrect polystrings. And they just argue that, so what Greville et al. Argue is that when tau is larger than 0.85, then 0.5 is the boundary between the correlation of any correct and incorrect polystrings. And based on this observation, because just as I said, like polystring is a special case for the Weyl operator Wx. So based on this observation, they can still use Bell difference sampling to sample the distribution for all the Weyl operator Wx. And they can filter out the incorrect polystrings because incorrect polystring will give you smaller than 0.5, and correct one will give you larger than 0.5. So you can still use Bell difference sampling with slightly more resource to solve this problem when tau is larger than 0.85 because there is a boundary. And actually, we start with this algorithm. We kind of show, this is not in the work, but we kind of show that you can improve their algorithm to make their algorithm work for tau larger than 0.7 by making some bound more tight. But this is also not the main story. Okay, so now what happens if we have smaller tau? Like what happens if we don't have tau larger than 0.85 or larger than 0.7? For example, if we have the unknown state to be 0.5 times all zero and 0.5 all plus, and without loss of generality, we can still assume all zero to be the correct answer and the remaining one to be the noise. So now let's do Bell difference sampling. What happened? We just find that the basis in IZ basis that correspond to zero, and the basis and the polystrings in IX correspond to all plus, they're equivalent because all of them are 0.5. And because just as we mentioned, Q is evenly distributed over stabilizer group. So you will find that everything will mix up. Like all the IZ polystring and IX polystrings are mixed up. So you cannot distinguish between IX and IZ polystrings. But what we can do is that after you do Bell difference sampling for many times, you can at least get one basis in the correct stabilizer group. Like you do Bell difference sampling for many times, you can at least get something like IZ, but you cannot get all IZ like the IZ basis. You can only get one basis. And Greville et al. So they have an exponential time algorithm because what they did is you sample polynomial times and you enumerate over all the independent sets, and this will lead to an exponential time algorithm. They solve this problem using brute force. So the question is, can we get rid of this exponential time algorithm? And here is the key idea for our work. It's guess, measure, and amplify. So we start again with this simple example, like 0.5 times all zero and 0.5 times all plus. And you perform Bell difference sampling once. So with some luck, you can get a correct polystring P. For example, you get one correct polystring, not the correct stabilizer group, but just one correct polystring P. P equals to ZII. And with more luck, you can get a correct guess for the sign. Sign means that how this P stabilizes this state. Here the correct sign is of course +1. So with more luck, you can guess the correct sign. And now we do some post-selection. We measure this input row in the basis of I plus minus P over 2, and post-select on the output on the plus outcome, which is the sign we guess here. And what we get, the post-select state is O0 plus 1 over square root 2 times 0 plus plus plus. Okay, this is an unnormalized state. But after post-selection, we boost the part for O0, and actually we amplify the fidelity between the new row and the true stabilized state, and the correct answer. We boost this fidelity. Okay, so sorry, there's something wrong, but okay. And we try to formalize this. So for general row, we perform a Bell difference sampling. With non-negligible probability, you can get a projector. Just in the previous slides, we get something like ZII. So you perform Bell difference sampling, you cannot immediately get all the stabilized bases, all the bases for the stabilized group, but you can at least get one basis, one polystring, and based on this polystring, you can construct the corresponding projector. And then you measure row on this projector, and do post-selection, and you get a post-selected state row prime. And for this row prime, the stabilized fidelity will amplify by a factor of 1 over trace pi row for the projector you get. So this is what we get by measure and amplify. But the problem is that we have no idea what is this factor. If trace pi row is very small, then after we do post selection, we actually amplify this stabilized fidelity by a large factor. That is what we want. But if this trace pi row is very close to 1, what happens is that the stabilized fidelity will largely remain unchanged or will only increase a little bit. How can we solve this problem? Before solving this, before talking about the solution, we need some preliminaries on the uncertainty principle, which says that for anti-commute Weyl operator Wx and Wy, you always have trace Wx row square plus trace Wy row square smaller than 1. So which means that suppose there is a high correlation basis. High correlation means that every W row here is large. If there's a high correlation basis for the correct stabilized group, then any incorrect polystring will anti-commute with one of them. And thus, for any incorrect polystring, it is low correlation. So let's combine this stuff with this factor, which means that if we have a small trace pi row here for a correct projector pi, if we have a small pi row, then we can amplify. That's what we want. If we always have big pi row, then any incorrect polystring will have very small correlation, and this will create a boundary. So let's formally talk about this. For general rows, again, we perform Bell difference sampling once and obtain P, obtain polystring P, and P is correct. That's what we assume. Okay, for case 1, P is low correlation, which means that trace P row square is small. Then this corresponds to the case in the previous slide when trace pi row is small, and then this will amplify the stabilized fidelity for the row after you do post selection. But what happens if we keep getting some high correlation P, corresponding to the previous slides that you always get some large trace pi row? Then when we do Bell difference sampling for many times, we get many high correlation P, and we can obtain a high correlation basis of the correct stabilized group. And because all the Pauli strings in this stabilizer group is of high correlation, so all the incorrect Pauli strings will have low correlation according to the uncertainty principle. So this will again create a borderline between the correct Pauli strings and incorrect Pauli strings. And we can use the previous filter by correlation strategy using Grivol et al. So no matter you get low correlation P or high correlation P, at least one of this strategy will work.
Can I just ask?
Yeah.
The sentence that you can assume P to be correct, how does that work? This seems like a strategy that works if you think that the P you got in the first place is true, then both cases are cool. But what if P you got in the beginning is wrong?
Yeah, but the argument is that as long as this tau is not so small, then as long as you do it for polynomial time, you can always, with large probabilities, sample at least one correct.
That makes sense. Thank you.
Yeah. So
I also have a question.
Yep.
Maybe also a comment for, if Lorenzo is around in the audience. But yeah, here goes. So this Pauli's whose expectation square is larger than 1/2. This is a group, right? Because they commute. Because if they didn't, then by this uncertainty relation that you show, they wouldn't be able to have larger than 1/2, the two at the same time. So this is a subgroup. And I think Lorenzo a couple of times mentioned that this subgroup of the stabilizer group of a state can be learned efficiently. So is this a general thing that a set of Pauli such that they all are larger, their expectation square is larger than 0.5, this can be learned in general, or is there something else that I'm missing, or is this general statement?
I'm not sure if I get your question. So what happens if? So are you arguing that?
Can I summarize your results by saying that you can learn efficiently the subgroup generated by all Paulis whose expectation square is larger than 0.5?
Mm-hmm.
Okay, so it can be stated like that, no?
Because if you have high correlation, like if for this row you have a high correlation group, then you can actually use the previous slide here. Not this gas amplify, but this algorithm. You get a boundary 0.5 between the correct Pauli string and incorrect Pauli strings.
Yeah, exactly.
And you are given the fact that there is such boundary. There exists such a high correlation group.
I see.
Yeah.
And it's always 0.5, no? So it wouldn't work for 0.4, for instance, or I think this is my question. If this 0.5
it will not work for 0.4 because for 0.4
exactly. Okay. Good. So then, yeah, this answers my question. So it's this 0.5 that I remember that Lorenzo mentioned.
0.5 is necessary. You cannot push it to a smaller value.
Okay. Sorry. I had my video off. I didn't realize. Anyways, thank you.
Okay. So this is actually the key idea for our algorithm, and the remaining part is we try to formalize what do we have now. The first step is you perform Bell difference sampling for like n over tau to the 4 times, and we can argue that after sampling for this many times, you can at least get some correct Pauli strings with high probability, and then you select the high correlation group, which are all the PIs you sampled here, all the PI that has high correlation. And of course, H is a correct stabilizer group by uncertainty principle. And with high probability, this will contain most of the correct high correlation Pauli string with high probability. But this is not the full stabilizer group. So there's no guarantee showing that this contains all the stabilizer group, but it is a subspace of the stabilizer group. Okay, so now what we do next is to test this H. If H really forms a stabilizer group, then we are done. And this case is really lucky. Like if H contains all the stabilizer bases, then we are done. But in this case, we're really lucky. And how to get the state psi? How to get the state phi? We only need to measure the unnecessary row on the common eigenspace of H once to obtain a stabilizer phi. We have phi equals the correct answer phi star with probability at least tau. And so you can always use like 1 over tau times measure to actually get the correct answer. And we just output this phi and terminate. But the problem here is that we cannot actually tell if phi is equal to phi star. So we can actually store all the phi we measure here in a candidate list. But anyway, if H really forms a stabilizer group, then we are done. But this is not always the case. Most of the time, we will find that H cannot form a stabilizer group. But at least H contains the correct polystrings. So the intersect between H and the correct polystrings is a subspace of the correct stabilizer group. So this is what we know. And recall that for Bell difference sampling, Q rho is evenly distributed over the correct stabilizer group. So if we choose V here to be H, and we consider the stabilizer group that is not sampled in H, then Bell difference sampling should have a large probability support on the remaining subspace. This means that with probability at least 0.1 tau to the 4, this is because what we are guaranteed, the fidelity between rho and phi star is larger than tau. So with probability at least 0.1 tau to the 4, if we perform Bell difference sampling again to generate a polystring, then with this probability, we can guarantee that this polystring is in the remaining subspace, and it has low correlation. Okay, so again, like if H is not, so step 2 means that if H is the full stabilizer group, then we are done. And now here we are talking about if H is not the full stabilizer group, then because Q rho is evenly distributed over the stabilizer group. So with probability 0.1 tau to the 4, if we perform Bell difference sampling again, we can generate a polystring in the remaining subgroup from H, like in the correct subgroup minus H. And we can sample another polystring in this stabilizer group. Okay. And we can go to the fourth step, is that after you get such a polystring, you can just do the measure and amplify trick. You can construct this projector pi and measure the state rho on this projector pi, and you post-select on a sign you guess to obtain rho prime, and you back to step 1 with post-measure state rho prime. And because P is low correlate, so we can actually always boost the stabilizer fidelity by a factor using this method. And there's a lemma showing that for the post-measured rho prime, the closest stabilizer state to rho is also the closest stabilizer state to rho prime. This is a lemma we prove. So let's draw a picture on this. The first step is to perform Bell difference sampling many times to find high correlation projectors. The second step is if the high correlation projector already forms a stabilizer group, then we are done. The third step is if it is just a subspace of the correct stabilizer group, it's incomplete, then we sample a low correlation projector. And the fourth step is we measure we measure rho using this low correlation projector and boost the stabilizer fidelity. So step 3 will succeed with probability 0.1 to the times tau to the 4, just as we mentioned. And every time the stabilizer fidelity is amplified by a constant factor, because we are guaranteed that for low correlation projector, trace p rho square is smaller than 1/2. So every time you can guarantee that the stabilizer fidelity is amplified by by square root 2. So you actually need log 1/tau rounds to boost the stabilizer fidelity to 1. And the overall success probability will be tau to the log 1/tau scaling for 1 turn. And we repeat for this many times, and this will yield the correct answer. We can boost the stabilizer fidelity to 1 with high probability. So that's how this 1/tau to the log 1/tau scaling comes from. Okay, this is a proof of the main theorem, and there's a byproduct for this main theorem. Byproduct is called least decoding, which means our algorithm can also output all the phi that is close all the stabilizer state phi that is close enough to the stabilizer fidelity. Formally speaking, is that we first introduce a definition, the local maximizer. A stabilizer state phi is said to be a local maximizer of rho. If for every neighboring stabilizer state phi prime. Oh, I think there's a typo. Okay, but if for any stabilizer state phi prime such that the fidelity between rho phi is larger than fidelity rho phi prime. Sorry, here is phi prime. So it's a local maximizer, which means that for if you choose a neighboring stabilizer state, then the fidelity will drop by a factor of 2, at least. And we also have like Q rho is evenly distributed over the correct stabilizer group. So for every local maximizer phi star, this inequality also holds. And our algorithm will actually return to a list of all these numbers of local maximizers that has fidelity at least tau to rho. So it's like our algorithm will output all the correct answers, candidates for the correct for the correct answers. And this is like least decoding in encoding theory. Okay, I guess I'm running out of time, so like we can roughly skip the agnostic learning for discrete product state, or like okay, maybe just very briefly talk about the results. So we kind of just show that this stabilizer bootstrapping strategy also works for agnostic tomography or other class of states. One example is this so-called discrete product state. Discrete product state means that for every qubit, we consider a discrete set K, such that any 2 distinct element in this K has fidelity at most 1 minus mu. And we call such K a mu packing set. And the agnostic tomography task here is that you are given an unknown state rho, and your goal is to output a sigma in this set K tensor n, such that it is roughly it roughly achieves the fidelity between rho and this set. So the agnostic tomography for this discrete product state set. And when K is equals to the set of 0, 1, plus, minus, plus I minus 1, this is also known as stabilizer product states. And here mu equals to 1, because for any 2 distinct elements, their overlap is like for mu is 1/2. For any 2 distinct element here, the fidelity between them are like 1/2. So the previous result in Greville et al., a different work, shows that there's an agnostic tomography algorithm that runs in n to the log 1/tau time, which means that for constant tau, their algorithm will be efficient. And okay, let's skip this. But anyway, we are we can do something very close, very similar to the stabilizer bootstrapping again. We can do the same stabilizer bootstrapping again, but every time sorry.
Yeah, there was just no, it's not important. Sorry.
So now the cracked projector is the product state at each side, but we are roughly doing the same thing. Okay, so the result is the complexity is like nk to the log 1 over tau over mu. So k here is the size of k of bk here defined here. The size of bk to be small k, and the final complexity is nk to the log 1 over tau. And this already, yeah.
Sorry, this case, so it's exponential in the case of sorry, like what is in the example k that you showed, like for
k cannot be too large if you fix mu, because k is because bk is a single qubit set.
Okay.
K is a single qubit set, and when you fix mu, k cannot be so large. Small k can. And in this case, like small k equals to 6, and mu equals to 1 over 2.
Okay, and if you say like the set of all product state, do you I mean, why is it challenging to do
all product state? Then you don't have this mu factor.
And it's challenging to solve with this technique, diagnostic tomography for the set of product state.
I don't think our algorithm can solve agnostic learning for arbitrary product state, but only for discrete. That's why we need this mu. It's discrete. But for general product state, it's not discrete. You don't have this.
While okay, I know that there is another paper that did also agnostic of product state. They just for comparison, do you know if that paper assume also some sort of discreteness? Like
no. So are you saying about that paper from Weiyuan Gong, Weiyuan Gong?
Yes.
I think their algorithm is completely different to solve general product state.
Okay.
Yeah, at least you cannot use this bootstrapping framework to solve the problem for general product state. They use something like sum of squares or solving some linear equation, so solving some sum of square systems, and some like highly adaptive stuff to solve to deal with their case for general product state. Yeah.
Okay, thank you.
And if you choose k to be 6 and mu to be 1 over 2, this already recovered the complexity in the previous work. This will also give you an algorithm for stabilizer product state, and that works in n to the log 1 over tau time. And this already recovered their result. But actually, we can do better. If we combine stabilizer bootstrapping with spell difference sampling, just as we mentioned in the stabilizer state case, we can improve the tau dependence to 1 over tau to the log 1 over tau again. So this is roughly like some improvement, because for their previous algorithm they can only work for tau, constant tau, but by combining it with Bell difference sampling, we can get efficient algorithm for tau equals to inverse sublinear again. Okay. And we also have some give some algorithm, give an agnostic tomography algorithm for states with high stabilizer dimensions. So stabilizer dimension of rho is a dimension of its stabilizer group. And here we can focus on states with stabilizer dimension at least n minus t, which refers to states with high stabilizer dimensions. And this will include the t-dot states with small t times t gates. So for any state that is prepared by a Clifford circuit plus small t numbers of t gates, the state will have stabilizer dimension at least n minus t. And for any state that is prepared by a Clifford state plus t over 2 arbitrary non-Clifford gate, the stabilizer dimension is also at least n minus t. So this is roughly an algorithm, an agnostic tomography algorithm that works for t-dot states. And in the realizable setting, just as I mentioned at the beginning of the talk, there's a polynomial n 2 to the t time algorithm. And in this work, we give an algorithm that runs in polynomial n 1 over epsilon times 2 to the t over tau to the log 1 over epsilon. So which means that if you assume tau and epsilon both to be some constant, then this algorithm is still efficient. And when t is like log n scaling, this algorithm is still efficient. And the solution for and this algorithm is still achieved by stabilized bootstrapping. Okay, I will skip this, but I guess I'm largely out of time. It's still obtained through stabilized bootstrapping. So just now I just roughly said that this stabilized bootstrapping framework also works for discrete product state and T-DOF states. And now let's go back to the stabilized state case, the lower bounds on this. So the first one is that because just at the beginning, and you guys ask a lot on what's the connection between agnostic tomography for stabilized state and magic estimation and stabilized fidelity estimation. There are some previous results in the pseudo magic paper showing that when 1 over tau is super polynomial, which means tau is super polynomial, then estimating stabilized fidelity efficiently is impossible. Because there's a pseudo random state ensemble that has inverse super polynomial fidelity with stabilized state, but they are hard to learn. They are hard to distinguish from true hard random state. So this means that estimating stabilized fidelity, at least in this scenario, is impossible for inverse polynomial tau. But estimating stabilized fidelity and agnostic tomography is different in this regime. So there's a gap between estimating stabilized fidelity and finding the closest stabilized state, because there's a super polynomial number of stabilized state that achieve such stabilized fidelity. So it's a little bit different. But we still show that it is impossible to do agnostic tomography test by another construction. Our solution is to show an information theoretic argument, which gives a lower bound of n over tau for agnostic tomography. We can just roughly think about the ensemble rho I equals to tau times the stabilized state phi I plus 1 minus tau times maximum mix. And this state will have a tau fidelity with stabilized state. And we can encode n squared bit of information here, because there are 2 to the n squared different stabilized states. But we can also show that each copy can, you just compute the von Neumann entropy here. Each copy can provide you at most tau n bits of information. So this already means that the sample complexity lower bound for learning this ensemble is n over tau. So this means that agnostic tomography for inverse super polynomially small tau is statistically difficult. And that's why we draw a cross here. But what happens for inverse polynomial? Actually, we have no idea. So statistically, it's easy. Using the algorithm from Greville et al. We mentioned at very early, Greville have a algorithm that works using inverse like poly n 1 over tau 1 over epsilon samples, but exponential time. So it is statistically easy, but it is computationally hard. So this might be a candidate for a so-called statistical computational gap, because inverse polynomial, it is statistically easy, but currently we don't know some computational easy algorithm.
Sorry.
Yeah.
Okay. No. Yeah. Maybe I wanted just to. You have a line here. No, I wanted to ask if already classical shadows solves the problem, but
yeah. You are just going to ask what I'm going to talk about.
Yeah.
It's really easy, because using polynomial numbers of samples, you can always estimate all trace phi I by shadow tomography. But it is computationally inefficient. And we also don't know how to reduce this problem to some hard problems like NP hard or LW or LP. And anyway, we don't know any reduction. In this work, we give a non-standard reduction, but I don't think that's a very valid argument. So, but we also don't know any efficient algorithm. So this might be a candidate for a so-called statistical computational gap. And it is a very common stuff, a very popular topic in learning theory, in classical learning theory. Yeah. And but it's still an open question. In this work, we reduce the problem to a so-called learning subspace with noise, with non-standard parameters. But actually, I don't think this reduction really says anything. Okay, so let's wrap up. Let's wrap up for this talk. Because like due to the time limitation, I skip some stuff. But I think the take-home message we will cover most of the part I talk in detail. The first is that the stabilized bootstrapping can be a framework that is helpful in both practice and theory. The guess, measure, and amplify trick. And we also talk in detail about agnostic tomography of stabilizer state. We show that our algorithm can work for inverse sublinear tau, and we show lower bounds for inverse superpolynomial tau, and we leave some gap here for inverse polynomial tau. And there are some open questions like, can we develop a single copy algorithm based on computational difference sampling for agnostic learning tasks? This is one open question. And another open question is like, can we develop agnostic tomography algorithm for more classes of states, like product states? And this is already covered by Ewing's and others' work, but their algorithm, I think, working n to the 1 over tau time complexity. So it's still open to it is still an open question to explore whether you can get some better algorithm. And you can also and you can also ask, can we get some agnostic tomography algorithm for other type of states, like shallow circuit states or states that can be prepared by bounded number of gates. Okay, that's all. And thank you for your listening. Yeah, and here are some reference, a lot of reference. Okay.